and welcome to Team C2 headquarters. Today what I want to do is talk a little bit about the flywheels, because we opted for that method of launcher on our robot. I want to talk a bit more about flywheel speed, theoretical flywheel speed and an actual flywheel speed, and how these things can help you in your robot design and seeing exactly what's going on, especially with regards to the efficiency of your flywheel launcher. So we're going to go through a few basic tests that we can do to see how fast our flywheel is actually running. I want to look at a couple of different things. Firstly, we've got the theoretical maximum speed of the motor and the flywheel. So the specification on the VEX site says that the no-load speed of the motor, so that is when it's just spinning in free air, there's no wheels or gears or any load attached to it. In that circumstance, it's 120 RPM. Now the gear ratio on the flywheel launch that we're using is 1:9. So the flywheels theoretically will spin 9 times faster than the motors, and so they will be spinning, if the motors can run at the full 120 RPM, they will be spinning at 1080 RPM. Now the reality will be different because there's losses in the system. We won't get the no-load speed on the motors, but what we're interested in is the actual speed that we're getting with our flywheel. So we're going to do a couple of things. First thing I'm going to do is going to test my motors under the no-load condition and see how close to that 120 RPM they run in the no-load condition. That's the first thing I want to see. The second thing we're going to do is what is the actual speed of the motors and indeed the flywheel. So when it's connected to my full drive system and the gearbox, what is the actual speed of the motor and the flywheel? And finally, I'm going to write a bit of code in RobotC to measure that as well within our software, and we can compare all the results. Okay, so here's our robot, and those two motors on the top there are the ones that drive our flywheel launcher. Our flywheel launchers run through this compound gearbox here, and it has 2 possible settings depending on the position that we put the motor in. It's currently connected to the 9:1 ratio, and it can also do a 27:1 as well by moving the motor to drive a different gear. So at the moment, this is the first stage, so the motor is driving this stage here, so we have this set of gears, and we can drive this shaft instead, and gives us an extra set for playing around with the 27:1 ratio as well. So we've got one motor for each side of the flywheel launcher. I've labelled them L and R for left and right because I want to keep track of each motor individually, because the specs might be slightly different on them. So it'll be interesting to compare the no-load speeds of the left and right motor and then the actual flywheel speeds of the left and right motor. That will tell me whether I've got losses in my gearboxes or whether there's some inefficiencies here, because if they both turn out to be 120 RPM or thereabouts, no load, and then when I actually connect them up to the gearboxes, I find that one's going quite a lot faster than the other. It may well be that I've got losses in the gearbox I need to be looking at, something's tight somewhere, so that can help me to improve the performance of them. So the first thing I'm going to do is I'm going to take these motors off and I'm going to connect them up to a little test bed that I've built. Right, so this is my test rig, just to check the no-load speed of these 2 motors. And so I've got my the left motor off my launcher here, the right motor off my launcher here, and I've hooked them up to this really simple little test bed, which is basically just 2 of the large 60-tooth sprockets, 60-tooth gears, and they're connected directly to the drive of the motor. So it's just 1:1. This shaft goes directly into the output drive of my motor. On this gear, what I've done is I've marked one of the teeth there quite clearly with a bit of white correction fluid. Same on this one here. So this is connected to my other motor, and I've put 2 little standoffs in this plate which basically give me a marker, so I can see a sort of a point of reference as the motor's done 1 revolution a minute. Sorry, one complete revolution. Now, later on, we're going to look at using a device called a stroboscope to help measure the speed, the rotational speed. These motors, when they're doing 120 RPM or thereabouts, that's roughly twice a second. It's not particularly fast. It's not really fast enough to warrant a stroboscope. I'm actually going to be able to physically count this because it's going to be slow enough for me to physically count. You may not be able to see it on the video because it depends on the frame rate of this camera. If I run up a program here, it's going to just turn both my motors onto full speed. So yeah, you can probably actually see that. You can actually just see the white marker whizzing round, and it's quite clear to see every time it passes this counterpoint here. That's my 1 revolution. So essentially you could sit and count them for 1 minute, how many revolutions it does in 1 minute, and jot that down. I don't want to sit and count it for 1 minute, so I'm going to count it for 30 seconds, and then I'm going to double it. So what I've got here is a little stopwatch, a little timer. Okay, so we're going to start the timer running, and I'm going to just count in my head how many revolutions each flywheel does. I'll do them individually because counting them both at the same time is going to be interesting. Do them individually, and I'm going to count the rotations of each flywheel in a minute. So get them running. And I'm going to start my timer and count the number of rotations in 30 seconds. So I've counted my no-load motor rotations. The left motor did 59 in 30 seconds, so give us 118 RPM. Right motor also 59, so it could just be my counting there. I mean, we're as near as can be the 120 RPM that we expect from the no-load speed of the motor. Okay, so what does that mean? Well, theoretically that means we can get pretty near our 1080 RPM flywheel speed, but what are we going to get in reality when we connect it up? So what I'm going to do now is put these motors back onto my robot at on the 9:1 setting on the gearbox. So I'm just going to pop those back on. So the motors are back on the robot, and now what I'm going to do is try and measure the flywheel speed. Now the flywheels are going 9 times faster than what the motor turns, and when the motor was spinning on our test rig, it was relatively easy to count 2 rotations a second, which is essentially what it was turning at. On our flywheels, we're going to go 9 times faster than that, and to count it with the eye is probably not going to be possible. So what I've done is I've marked with the white paint again a mark on each flywheel, so just a single mark on each flywheel. And in the ideal world, what we would use to measure this is a device called a stroboscope. So I've got a link in one of the documents on the site to a video explaining how stroboscope works as a separate thing, so I'm not going to explain how that works here. Now I don't have a stroboscope, so I'm going to kind of simulate what a stroboscope does by using this function generator, and we've got an oscilloscope there as well, so that we can kind of see a bit about what's actually going on, what the function generator is doing. So the function generator is a device. Hopefully you'll have one of these in school, so you can simulate this if you want to have a play yourself. It's a device that generates waveforms. This one can generate a square wave, sawtooth wave, or a sine wave. We can control the frequency of that waveform, and we can control various other parameters as well. I've got the output of that hooked up just to an LED, and then we're also measuring that with the oscilloscope, which at the moment is just showing a bunch of noise because nothing's switched on. But let me turn the function generator on. And at the moment it's generating a square wave of 1.7 hertz, which is the slowest that this function generator will actually go. I can't turn that down any further. So we'll have a look at what that looks like on the oscilloscope. There we can see the waveform. Just adjust that a little bit. So there we can see the waveform that I'm using, and these peaks represent when the LED is switched on, and these troughs represent when it's switched off. So we're switching it on and off quite slowly, and there's the actual LED there. You can see it flashing away. And what I can actually do is by increasing the frequency, so let's turn this up to 7 Hertz there. Now we can see that the peaks in the waveform have got much closer together, and the LED is now switching on much quicker. It's on for less time than it's off. I've got this function generator set up like that because I only want a very short flash of light, because when the wheels are spinning, I don't want to illuminate this mark for too long. If I have the light on for too long, it'll be a bit blurry, because you'll see the eye will see that the mark as it travels through quite a few degrees of rotation. The shorter I can flash that light on for, shorter and brighter I can flash it on for, the clearer this image will become, so that the more accurate I can be with my measurement. So how is this going to be any use? Well, what I'm going to do is put the room into darkness, light the wheel up with the LED like this, and I'm going to increase the frequency of that flash until this mark appears to be stable, and then that's going to give me a reading in hertz as to how fast the LED is having to flash, and then I can work out the revolutions per minute from that. So I'm going to go and switch the lights off and get the robot fired up and give it a go. If you're doing any of these tests, make sure that your batteries are fully charged, because it's going to have a big impact on how fast your motors are spinning, how much power you've got available to spin the motors. And it's an important thing from a competition point of view as well. I think more so than ever. The VEX IQ batteries last a long time. When you're running things like the Clawbots that you make from the starter kits. However, in a competition environment, when you're running 6 motors, especially when you're using a lot of load and you've got flywheels running for the whole match, the battery life is going to deplete. It's going to be less than what it would be on a Clawbot. So just bear that in mind. You should recharge your batteries as much as possible between matches. Right, so I'm not sure how this is going to work. I don't really have enough hands, but let's give it a go. So in the darkness now, we've got my flashing LED there, which I'm going to try and hold with the same hand that I'm holding my phone with. See if I can manage this. Okay, so now if I fire my flywheels up, and the idea is I increase the frequency of the LED until we get the appearance of the white mark being stationary. It's slowing down, so I'm increasing the frequency, slowing down. I must be pretty close now, there it is. Okay, so it's pretty stationary there. Okay, so what's our value? So it's about around 16 Hertz. I'm probably going a little bit too fast now, as it's going ever so slightly backwards. But around about 16 Hertz. And here are the results from the stroboscope test. And you can see there that our left flywheel was doing 840 RPM. And our right flywheel 976 RPM. We can actually add the original motor speeds as well, the no-load motor speeds. They were both 118. RPM. So no load, they were both the same. The left flywheel is going slightly slower, so we've probably got some losses in the left flywheel. So what we're going to do now is run another test, final test. And this is the Robot C, the coding test. So what we've done here is put a little program on the brain, and what it does is it uses the integrated motor encoders that are actually within the motors themselves. And what we're doing is very similar to our other test that we've done. We're going to measure the rotation, the number of rotations over a short period of time. So in the case of this program, 10 seconds. And what the program does is it winds the flywheels up to speed. Once they hit full speed, it resets the motor encoder count for each motor to 0 and starts a 10-second count. And at the end of the 10-second count, stores the motor encoder value. And what that value is a number of degrees that the motor has turned in that 10-second period. So we divide that then by 360 to give us the number of complete rotations that it's completed in 10 seconds. And then we multiply that by 6 because we want 6 lots of 10 seconds to give us a full minute. So that's how many rotations we've done in a minute, which is our RPM, revolutions per minute value. That's what the program does. And it should give us a fairly accurate reading. Basically, we get the revolutions per minute of the motor, and then we multiply it, the code will multiply it by 9 for our gear ratio, because it's 9:1, and give us a flywheel value. And then print it to the screen of the brain. I'm not sure how clearly you'll be able to see it, but we'll give it a whirl. So, I'm going to fire up the program. Let's just try and get the camera in. A bit blurry, but you can kind of see it. There it goes, it's winding up, we're getting the flywheels up to speed. Once the flywheels at full speed, there we go, now 10 seconds is starting, and it's going to take a value at the end of that 10 seconds. At the end of the 10 seconds, slow the motors back down and display the results. So what it's saying there, I'm not sure if you can quite see that, the left motor was doing 100 RPM, right motor 110 RPM, and at the flywheel 900 RPM on the left and 990 on the right. So let's go and compare that to the actual results. We had 900 RPM on the left, 990 on the right, and 100 RPM at the motor, 110. Right, there we go. That's our final results. So there's some theoretical values in here. So this is a no load speed, whereas this is a loaded speed. This is a loaded speed, as is this. So this one is a theoretical value, but other than that, we've got some results where we can certainly see some correlation. So in all cases, the left is definitely running slower than the right. And actually these values aren't that far out. When I was using the stroboscope values, I did round things up pretty drastically. So you know what, the left flywheel was probably about 14.2 or 3 hertz, and I just rounded that to 14. So that would probably account for the differences between these. But it shows that the pattern is correct. My left flywheel is less efficient, is performing poorly compared to the right flywheel. So I probably need to look at the look at the left gearbox and see if there's any losses in there and try and improve that. So hopefully that gives you a bit of an insight into ways that you can measure your flywheel speed and look at the efficiencies of your gearboxes and the efficiencies of your flywheels. So the methods we used there was the basic test bed to see how fast, just to count visually the motor speed. We used the stroboscope, the homemade stroboscope, and finally the Robot C code on the brain itself to get actual flywheel speed. So have a look at the resources on the site, and hopefully that will give you some pointers for flywheel design.